Hi there, my name is Mahsan Nourani, and on behalf of my co-authors, I'm here to present our paper, Anchoring Bias Affects Mental Model Formation and User Reliance in XAI Systems. Metaphorically, machine learning models are referred to as black boxes due to their lack of transparency. These models make some predictions based on the inputs without properly justifying their predictions. Following the same metaphor, researchers propose opening the box and making the model's decision-making more transparent by providing explanations. With the explainable AI models, explanations can help users understand the rationale behind model predictions and how their actions affect the model outcomes. This is also called human mental models of how the algorithm works. In this paper, we focus on user mental models in XAI systems. To build more accurate mental models, users need to experience and be exposed to both model weaknesses and strengths as they use the system. However, in our previous research, we observed that the order of encountering errors can influence impression formation and trust. In that regard, users who were exposed to model weaknesses early in their usage tended to mistrust the model and had problems calibrating their trust over time. On the other hand, with positive first impressions that were caused by seeing model strength early on, users tended to have a better judgment of when to trust the model. Interested to study the impacts of first impressions on mental model formations, we formulated two high-level research questions. First, we wanted to learn how do positive and negative first impressions can affect users' mental models, and second, can explanations help mitigate a potential anchoring bias or not? For the purposes of this study, we chose the video activity recognition domain, which has many real-world applications such as security surveillance. Specifically, we focused on activity recognition in cooking videos where people perform cooking activities in a kitchen setup. We define each activity as a combination of actions, objects, and locations. For example, in this frame, the person is moving pineapples to a plate, with move as the action, pineapple as the object, and plate as the location. We trained an XAI model that allows users to query the model to determine whether an activity takes place in a video. The model is able to answer the query and provide explanations to justify its rationale. So here is an overview of our XAI system interface. On the top, users are able to build their own activities to query the model by selecting actions, objects, and locations from a list of defined vocabulary. When the user searches for an activity, the system would categorize the available videos based on whether activity was found in each video or not. For example, the top 4 videos shown here where the model found cutting cucumber is taking place, while the videos on the bottom are those that model did not find the activity in. Upon clicking each thumbnail, a more detailed overview of the video pops up that shows the video, the response, and the model's explanations for its prediction. For the explanations, the model shows the segments of the video used to find the prediction. For each of these segments, the model shows its top 3 detected activities as well as the individual activity components found within the segment. We designed a hypothetical scenario where the kitchen staff had to follow a set of kitchen policies and guidelines, and users' task was to understand whether each of these policies are being followed or not. An example policy is that employees need to wash their hands before they start cooking. We designed 4 policies to reflect systems' strength and 4 policies to reflect system weaknesses. We altered the order of policies to control the order of observing system capabilities and weaknesses. We designed a 2x2 user study with 116 participants with 2 independent variables. The first variable is policy order, where half of the users observe weakness policies at the top of the list, while the other half observe the strength policies at the top. We also altered whether users had explanations or not. At a high level, participants first completed the policy verification task to build a mental model of the system, where we also measured usage and human-machine task performance. After completion of the main task, we measured participants' mental models through prediction tasks, which is a common method in XAI research, and the user is asked to predict models' behaviors on different inputs. Our results from the main task indicate that while participants with positive first impressions used the system significantly more, they also made significantly more errors. This seems to be due to an automation bias, where the users tended to rely heavily on the system even when the model was wrong. On the other hand, with negative first impressions, participants reported they used the system significantly less and made less errors simply because they tended to rely more on themselves than the system. For this study, we used two mental model questions. For the first question, we selected 8 activity components that could be actions, objects, or locations, with half of them being model weaknesses and half of them being model strengths. We asked participants to estimate the model's detection accuracy for each of the 8 components. Also, we asked users to rate their confidence in their estimations. Our results from the first mental model question indicated that users tend to have a more appropriate estimation of model strength while being more confident about their estimations with positive first impressions. Their counterparts, on the other hand, significantly underestimated the model capabilities while being less confident about their mental models. In other words, those with negative first impressions were significantly more skeptical of the model capabilities while not being so confident about their skepticism. In the second mental model question, participants were provided with 12 pairs of frames and queries and were asked to predict whether the model would match the frame to the query. They were also asked to rate their confidence. The users' aggregated predictions showed an average of around 59%, indicating that the estimations were no better than randomly guessing. The results from the users' reported confidence showed significant differences. First, without explanations, those who had a positive first impression were significantly more confident about their estimations. For those with negative first impressions, those with explanations had significantly higher confidence. Based on our results, guessing with high confidence can be an indication of overconfidence. This overconfidence took place in 2 situations. First, with positive first impressions and without explanations, and second, for those with negative first impressions with explanations. Thus, we can see that positive first impressions or explanations can both lead to users' overconfidence in their mental model. So, the main takeaways from this study are: the addition of explanations was not enough to counteract the strong effect of early impressions. Also, with explanations, users might think that they understand how the model works when in fact they do not. We demonstrated that anchoring bias can affect overconfidence, user over or under reliance, and formation of mental models. As previous research in various fields, such as human-centered AI and psychology, demonstrates, overconfidence and misreliance can be dangerous. Thus, future research efforts can propose techniques to mitigate the human biases through making users aware of their biases, preventing users from forming new biases, and helping users to rectify their existing biases and misconceptions. For more information and details about the system, study, and the results, please refer to our paper. With that, I would like to take a moment to thank all my co-authors from both University of Florida and UT Dallas. Thank you.